So, hello everyone, I am Dr. Sachidanand Sen, working in the Department of EEE, SR University as Associate Professor. And the subject today we are going to deal is battery management systems. In lecture 1, we are going to learn about the sustainability in battery technologies. So, sustainability in battery technology. So, introduction. So, as we are all aware, with the increasing penetration of renewable energy sources, so batteries are the central to the clean energy transitions. It powers the electric vehicles, renewable energy integrations, and consumer electronics like your laptops and mobile phones, all these things. The global battery market is projected to exceed $400 billion by the year 2030, means in the upcoming 4 to 5 years. And in this, mainly it will be driven by the electric vehicles. So why sustainability in electric vehicles, or in fact the battery matters? The conventional battery production is resource and energy intensive, right from the extraction of the precious rare earth materials which are used as raw material for the manufacturing of the battery, and the whole process itself is quite energy consuming. So it is energy intensive as well as resource intensive. The environmental, social, economic challenges are existing across the life cycle, means right from the extraction to the usage and to the production, then usage, then end of the life cycle disposal. So whole cycle is considered to be the life cycle. So in this, the steps involved are raw material extraction, then manufacturing or the production step itself, then operation or in life usage, and at the end of the life. And once the battery life is ending, definitely we have to go for disposal. So safe disposal is also a concern. It should not become a hazardous compound for the environment, whether you are dumping it under the ground, whether you are putting it water, it should not create problem for the organisms that are surviving below the earth or under the water. So the goal mainly related to the sustainability in the batteries are to develop sustainable battery technologies that minimize the environmental impact and ensures ethical sourcing and maximize the circularity. So minimize environmental impact, as I just now mentioned, that it should not be hazardous to the any of the living organisms, whether below earth or during the usage, even human or animals. It should not create huge amount of pollutions, or end of the life disposal also, like under the water or cleaning process is there. So all these things, it should not be hampering the environment in any way. Then ensures ethical sourcing. So means it comes under mining, the way we are extracting the minerals. It should not create the problem at that extraction stage itself, means we should not go for deforestation, then digging of the land masses, then extraction of that minerals. Okay, so this process should also do not create any harmful impact on the environment. So maximize circularity means as long as possible we should be able to reuse a battery again and again. Okay, so first life cycle, it is mainly considered for electric vehicles. Then once the electric vehicles usage is over, then we can go for some other applications. So that also need to be considered. So those things we will see in more detail in the subsequent classes. So now we will see this comparison between, suppose this is a lithium ion battery and suppose we are having a balance between the performance and sustainability. So in performance, what we are expecting from a battery, that are the safety, it should be safe, it should not catch fire easily. Then lifetime, it should be able to be work up to 5 years, 7 years, 10 years, as long as possible, depending upon, of course, usage is there, but it should be long life. It should have a long life. It should not ask for frequent maintenance. It should have better power density, better energy density. So all these things. Then fast charging. Of course, we don't want to lose any time, okay, in traveling. so that we will reach the destination at a longer time. So everybody is expecting the battery should be charged as fast as possible. Similarly, number of charging stations should be more often, it should be more frequent, very close by. Okay, so these are some of the expectations. So performance wise, and power density means power density in a very short span of time, it should be able to charge or discharge. It should be able to discharge huge amount of current, such as like during the process of acceleration. Suppose huge amount of current is required for the electric motor, so the battery should be able to support that quick acceleration. Similarly, the energy density. So in energy density, as it is expected, the storage capacity of the battery should be as much as possible, like kilowatt hour storage capacity. So in a small compact volume, the maximum rating or storage capacity should be more and more. That comes under energy density. It should occupy minimum space and maximum storage capacity. Now coming to the sustainability. So in sustainability, what are the things or the aspects that we need to consider is second life. Second life means after the first life, suppose electric vehicle, this is one of the important life, because it is, people are traveling in that, it is, our life is depending upon the working of the battery. So when the health of the battery is deteriorating, if it is degrading over a period of time, so gradually once it is going below 80%, so what is state of health and all we will discuss in the subsequent classes or the lectures. And second life means once the electric vehicles performance is degrading below, suppose say 80%, then we will be able to use those batteries for some stagnant or stationary work like renewable energy integration and all. So element abundancy and material accessibility. So in this renewable, the materials that we are selecting for say that manufacturing of the battery, they should be abundantly available. They are easy to extract materials, and there is no shortage. There should not be involvement of huge amount of import from some other countries. So that kind of things are coming under abundance and availability and accessibility. So renewable energy resources, carbon footprint. So like it should not emit harmful gases. Okay, so because of global warming, greenhouse gases, those effects. Okay, so ozone layer depletion, it can create lot of problems. So carbon footprint should be minimum. It's basically the carbon monoxide and carbon dioxide emission should be as low as possible. Then recyclability. The battery should be able to be recycled. Recycled in the sense the components like electrodes, electrolyte, and then terminals positive, the outer cell, every components can be cleansed properly. They should be able to reprocessed, refabricated, and these can be further reused. So that comes under recyclability. So if these features are there, so there definitely there has to be a balancing between the performance expectations and sustainability. So it may not be always true that a battery which is very good in performance is also a very good in sustainability. So these things need to be taken into account. So coming to ecological optimized. Okay, so a same thing is also depicted here, like performance, what we are expecting from the battery, and sustainability. So these things are also now coming to the alternate battery technology. Okay, stationary applications that just now I mentioned. In the second life of the battery, we are expecting it to be useful in integrating the renewable sources, because renewable, suppose say this is wind turbine, similarly solar panels will be there. So if they are being used, definitely power generation intermittency is there, because the fluctuations in the sunlight, similarly fluctuations in the wind speed, based upon that the power output will be degraded or reduced proportionately. So that deficiency should be able to be compensated with the help of batteries. Similarly, there will be time instance where the generation is surplus. Suppose peak summer, during peak hours, sunlight will be more, so power generation will be maximum. And suppose load is less, during that time we can charge the batteries. Okay, so these things are quite useful. And similarly, wind turbine, suppose the wind is excess of the rated capacity, so power generation will be more. So during that time, surplus generation can be stored in the battery, and when the deficiency of the wind speed is there, then we can use the stored energy from the battery to supply to the grid. So all these things are coming under the performance and sustainability balancing impact. Now coming to another perspective, sustainability is if we are able to reuse a battery again and again. So that type of batteries are coming under rechargeable batteries. So here what is the environmental impact and all we will see in a brief manner. Okay, so environmental impact. So rechargeable batteries emit 28% less greenhouse gases. So almost 28 to 30% reduction in greenhouse gases is there, and their disposal over time, okay, throughout the life cycle. So proper recycling prevents the release of harmful metals like cadmium, nickel. These are all hazardous elements for the environment. So that need to be minimized. They should not be directly dumped into the ground. Okay, so using rechargeable saves up to 11 times the energy they consume. So rechargeable batteries, we will be not only saving the components or the battery, we will be able to extend that life expectancy, and we will be able to reduce the emissions. Then life cycle of the rechargeable battery. So as already mentioned multiple times, almost 1000 times it can be charged, recharged, and there are certain rules, 50% charge rule, the most optimal range of battery charging will be 20% to 80% range. So you should not connect it to a charger until it is reaching below 20%, or you should not, you keep it in charging mode if it is crossing 80%. So like that, there are a lot of theories in that. So they use 23 times less non-renewable natural resources than disposable batteries. So rechargeable batteries can be used hundred of times. Okay, reduced wastage. Similarly, disposable batteries contribute to toxic waste when not properly recycled. So only one use is there. So even if you use once, after that definitely you have to go for disposing that one. So how many components you will be disposing throughout your application, so throughout your purpose. So that is also important. Rechargeable batteries, once you are purchasing, you will at least run it for 2 years, 3 years, depending upon your usage cycles. So cost effectiveness, definitely rechargeable batteries will be costly at the first as compared to disposables. But over a period of time, definitely you will recover the money, and for multiple usage, it will be sustainable also in the long run. So cost effectiveness over times, it can save up to 200 pounds by switching to rechargeables for high drain devices. Once rechargeable batteries can replace up to 300 single-use batteries. So you can say like rechargeable batteries, one rechargeable battery is like having 300 disposable batteries. Then in rechargeable batteries, almost 90% of the batteries can be recycled, conserving the precious resources. Follow 4 simple recycling steps. So use, tap, find, recycle, and recycle responsibly. So these are the steps involved in recycling. Similarly, in this, choosing the right battery, if disposable batteries we are considering, proper battery selection should be there. Consider usage like high drain devices like cameras benefit most from the rechargeables. Okay, eco-friendly choices we should be making. Track record of the environmental responsibility, and all these things need to be also considered into factor. So this is all a glimpse about the rechargeable batteries and its environmental impacts inside. Okay, now coming to the environmental footprint of current batteries technology. So what are the existing batteries technology and how it will impact the environment, that we are going to discuss. So lithium mining. So raw material extraction. So right from the very beginning, lithium mining, high water consumption is required, such as Atacama Desert in Chile. Okay, so this is a place where the materials are extracted. So lithium mining is also a process where we are consuming high amount of water resources. Similarly, cobalt mining. So in cobalt mining, what is the problem? So environmental damage, it is creating a huge problem in damaging the environment. Okay, so damage the environmental social issues. So as cobalt, nickel, these are all hazardous elements. So to extract them from the ground, we are or the peoples, mostly some mafias, they will be dealing with child labors, like in Congo, in Africa. These are a huge social problem. So they will be exploiting the children to extract these minings or these hazardous minerals mining. So nickel mining. So in nickel mining also it contributes to deforestation, greenhouse gases emission. So all these materials like lithium mining, cobalt mining, nickel mining, they are having definitely some form of impact, mostly in harmful way. So high water consumption, environmental damage and social issues. So contributes to deforestation and greenhouse gases. So manufacturing challenges. So high energy consumption in electrode production and cell assembly and drying. So in manufacturing cycle also, not only during the raw material extraction, but also during the manufacturing cycle, we are also having some issues like high energy consumption in electrode production, the material which is used to produce the electrode, then assembly of the cells, then drying. Of course, that liquid electrolyte will be there, so some form of drying is also required. So some solvents used like N-methyl to methyl to pyrrolidone. So this N-methyl to pyrrolidone is also one type of chemical that is having some environmental and health concerns. So that also need to be considered. So this is the issues that we can face during the manufacturing stage. Now coming to the usage phase. So battery enables decarbonizations like electric vehicle and renewable energy storage usage will be increased. Okay, so most of the usage phase, the batteries that we are using are beneficial during the usage stage and they are carbon negative mostly during this stage only. Okay, but the only thing is that suppose it's a rechargeable battery, then we will be using charging depends on the grid mix. So the electricity that we are going to use to charge the battery, from where that electricity is coming, whether it is generated from thermal power plants or fossil fuel based, or it is from renewables energy sources like solar, wind, hydropower, anything. So that energy mix, the percentage of thermal and percentage of renewables, that also has to be accounted for during this usage phase. Now once the battery usage is also completed, end of the life concerned. So during the end of the life, limited recycling is there. So only 5% of lithium batteries are recycled today. So landfilling leads to toxic leaching of the material. So like problems like very less percentage of battery are being recycled. So maximum of the battery are being thrown like that only, and they are at the end of the day they are going into the landfills and toxic leaching material. They are releasing some gases, contaminating the underground soil and underground water also. So these are the complete environmental footprint of a battery. So you cannot say that the battery electric vehicle that we are using is completely green. Mostly it is in the use phase only. So before usage, manufacturing and extraction, mining is involved. After usage, end of the life cycle concerns are there. So all these factors also need to be considered to know the overall impact of environmental impact of the batteries. So here this diagram shows the representation in a proper way. You can see the material extraction phase is there, then manufacturing will come. In manufacturing, raw materials mostly we are using iron, cobalt, manganese, okay, nickel, then copper, aluminium. So these are all extracted materials from the earth. So mining is definitely there. Then in the usage phase we are using electric vehicles for the first use, because top quality battery is used for electric vehicle. Once the battery's life is degraded, then we can use it for second hand usage or second life usage, like if when the battery will be retired, like lithium ion based batteries will be retired when the state of health is below or equal to 80%. Okay, so in that they will be used for mobile phone towers at home. Okay, so echelon utilization, so some second hand utilization will be done. And suppose now further it is degraded, if the state of health, the energy retention capability of the battery is suppose now less than 40%. Okay, so if it is now less than 40%, then we will be going for recycling. Then means the further usage of the battery is not considered to be efficient enough. Definitely we will go for dismantling and recycling. So that is the last stage. So this whole cycle is involving some form or other way of environmental impact. So that comes under the complete picture of analyzing the sustainability impact of the batteries. So the pathway towards sustainable battery technology. So what are the things that we need to consider are material substitution and resource efficiency. So in material substitution and resource efficiency, what are the things that we need to consider? Cobalt free batteries. So we should prepare batteries where the use of cobalt is minimized or it is free of the cobalt, like lithium iron phosphate. So LFP, Fe stands for iron and phosphate, P offered. So here is a alternative to reduce dependence on the cobalt. Similarly, high manganese electrodes or cathodes we can create. So it is of low cost, and manganese is also considered to be an abundantly available material. So definitely it is easily available, so cost will be less, manufacturing will be easier. Okay, silicon anodes. So this is also one type of material that we can consider to prepare the anodes. So higher capacity than graphite, potentially reducing the resource usage. So definitely some materials can be replaced, proper resource efficiency can be enhanced to reduce the impact on the sustainability factors. Then green manufacturing processes. So in the manufacturing itself, we should follow some green processes like use of water-based electrodes processing instead of toxic solvent. We should not depend on chemicals as much as possible. Okay. Then reducing the energy intensity in the in drying of the coating. So the coating that we are doing in over the electrodes, okay, anode and cathode, even in the outer cell. So there should be materials that are used which are not harmful, which are not emitting any form of gases. So intensity in drying and coating, okay, energy intensity should be reduced. Then adoption of renewable energy. So large solar powered renewable energy, wind power or hydro power based manufacturing facilities should be used, like gigafactories, like Tesla gigafactories. Mostly it is powered by solar panels. So in the manufacturing process itself, the electricity that we are using for the production of the batteries, in that itself we are not trying to use the electricity which is coming from the fossils. So this is also one of the advantages, and also a contributing factor towards a green sustainable battery technologies. The other things that we also need to consider are battery longevity, like efficiency. So as long as we are able to use a battery, so we don't need to produce another battery. So means there has to be some technologies which will extend the life of the batteries. So extending lifespans through advanced battery management system. So like we have to consider the battery management systems. What is that battery management system? Again, we will see in details, and it is nothing but a hardware and software integrated system which will help to operate the battery in a optimal condition. Okay, proper charging and discharging cycle should be there. Current voltage over limit should not be crossed. So temperature should not be crossed. That it also considers thermal management. So these things also need to be considered, and all these things comes under the battery management technology. So fast charging optimization. So in fast charging optimization, what happens? So charging speed should be improved. So to reduce the degradation, it should not degrade the batteries, and frequent charging should not be also done. Okay, so second life application, there has to be some alternate usage of the battery once the electric vehicle use is gone. Once the battery is below 80% of the state of health capability, it should be definitely used for some other application. So second life application of EV batteries is in stationary energy storage. So stationary means, already told you, vehicle is a mobility, it is a moving motion, in motion. But if the battery we are using in stationary standstill position to integrate solar, to integrate wind turbine, so definitely even if its state of health is quite low, means up to 40%, still it will be able to contribute definitely for the application or integration of the renewables. Okay. Now coming to the main phase of the sustainability, that is circular economy. So what are the perspective that we will learn? So recycling. So in that comes under circular, means there has to be a recycling of the, then means whatever the materials you have used, some portion will be, you should be able to extract, and you should be able to reuse, or it's like refurbished. You are able to reuse the material again and again. So that recycling technologies are broadly 2 to 3 types, like pyro metallurgical. Pyro means fire, so smelting, okay, but it is energy intensive. So if you are just burning or heating the components and melting them, okay, then you will be able to reshape them into different items. So that smelting process, that pyrometallurgical means fire based, is energy intensive. Then another one is hydrometallurgical. In hydrometallurgical, leaching metals, okay, using chemicals they are used, okay, more efficient. So leaching metals, like you are using harmful chemicals to clean the suppose electrodes, to clean the electrolyte portions, okay, dendrites that are being formed over the surface layers. So these things we are using high pressure, hydro based, water based. So that is also one of the things. Then direct recycling through hand or through some machines, you are breaking them, opening them, okay, so recovering cathode and anode material without breaking them down fully, okay, designed for recycling. So more and more batteries should be designed in such a manner that designed for easier disassembly and reuse. We should be able to reuse the battery again and again. So this depicts the complete representation. Same thing previously also we have seen, like raw material extraction, manufacturing, usage. Okay, if the battery is completely waste, you should go to the waste. If it is repurposed, it can be sorted. Again, you can go for second life. Okay, if not, then once the second life is over, in second life, already mentioned, like renewable sources and integration, these things we can use. Then disassembly, we can go for testing, sorting, and reassembly operations. Okay, so remanufacturing, you can remanufacture some portions, you can extract and go for the manufacturing stage also. Getting, so this is a complete circular economy. So this comes under policies, standards, and industrial trends that we are being following in this battery technologies. Okay, so right from manufacturing, raw material extraction, manufacturing, usage, then if it is damaged or something low quality, it will go to the direct wastage. Otherwise, it will definitely go for second life. If not, then it will be go for recycling. So this is the complete cycle. And so these are the processes that are showing the recycling process, like already mentioned, pyrometallurgical, burning in fire. So you will extract the components. Then hydrometallurgical, again you will extract the materials. Okay. Then repurpose some of the batteries. Okay, if you are getting, you can repurpose, you can use it for renewable sources integration and all, reducing residues and waste after second life. Once the second life is over, then you can go for landfilling and all. Okay, direct disposal and all you can go. So these are the different scenarios that we have discussed regarding the circular economy of the batteries. So now coming to the emerging sustainable battery alternatives. So in emerging sustainable battery alternatives, so what are the replacement of the presently lithium ion is considered to be the best possible in terms of cost, production and performance and all. So in future, what are the upcoming trends? So that we can analyze is like a solid state battery. So use solid state electrolytes. So these are something which will use solid state electrolytes um, safer because liquid is not there, so leakage issues won't be there. Safer, higher energy density, a longer lifespan. So it is safe, its energy density is more, and lifespan is also more. And it is in the very initial stage. It is not yet been commercialized that much. It is, I think some company, Japanese company is working on this one. So reduces need for flammable solvents. Okay, so we don't have any liquid portions. Then sodium ion batteries. So sodium is easily available, abundant material is there. So resources compared to the lithium. So low environmental impact and cost will be there. Okay, already commercialized. It is already commercialized by Kettle. So this is one of the battery company from US, I guess, and they are being already commercialized lithium-ion battery for stationary usage. It is not, it does not have high energy density. Means it's a high volume substance, but it can be definitely suitably used for uh, stationary purposes, not in the electric vehicle, because electric vehicle the space for battery is limited. So there we need for high density, high energy density materials. Now, metal air batteries like zinc air, aluminum air, so some substitute low cost, okay, high theoretical energy density, use abundant metals, okay. Then challenges and challenges are like rechargeability and durability. So these are the things that are also coming into picture. So solid state batteries, sodium ion batteries, low cost, or some metal air based batteries, which are all, although you can say in very early stage of implementation. Now, pathways towards sustainable battery technology. So what are the different aspects where we can implement the circularity in the batteries? Okay, so that we'll see. So improving total green merits like materials and system design. Okay, circular economy, securing transparency, some policy changes. So these things we can be implementing. So eco-friendly material selection, as much as possible that should be done. Sustainable synthesis process, that manufacturing process, extraction process should be free from involvement of fossil fuels and all. So design for end of life, recyclability, safety and environmental compatibility, energy and resource efficiency. So eco-friendly material selection, uh, sustainable synthesis process, design for end of life means once it is in use is over, definitely some recyclable policy should be there. Definitely second life usage will be there. So these are all coming under the principles of green batteries, sustainable technologies. Okay, in the right from extraction, right from production using renewable sources and all, safety and environmental compatibility, all factors need to be accounted for. So some more fun further emerging battery technologies can be like redox flow batteries, which is vanadium and organic based. Okay, so it is having long cycle life. So although we will not go into the details of these things, so long cycle life, scalable storage is there. Okay, these are mainly stationary and the chemical industries where the vanadium is coming as a byproduct or secondary product. These things can be used over there. Okay, suitable for grid scale application. As I already mentioned, stationary means solar farm integration, wind power wind integration. So large size in megawatt range of batteries we have to install. So that is possible with the help of rechargeable or redox flow batteries. So organic flow batteries, such research to reduce the reliance dependence on the rare earth material. As we are decreasing the dependency on the rare earth materials, definitely we are contributing more and more towards sustainability. So bio-inspired and organic batteries. So bio-inspired also, this is also at a very initial stage that I will, anybody can argue. So organic redox material molecules derived from biomass, potentially biodegradable and recyclable. So these are also some possible alternate and emerging sustainable battery technologies. So I think same things are depicted over here. Danger for throwing away lithium. So what are the different harmful things that we can face because of the negligence, okay, toxic chemicals, lithium batteries leak environmental contaminants like already mentioned cobalt, manganese, nickel, okay, lithium salts. So they will be mixing up with the underground soil, water, they will contaminate, and once we are drinking that water or we are growing some food over that land, definitely it will cause some problem. So harmful fine particles like some gases also emitted, then fire hazards can be done, it can contaminate the water. Lithium ion, they can transport the hazard chemicals, okay, so these problems can be happening, dumping of the wastage into the water and all, okay, so reaction mechanism, okay, dendrite growth, so lot of things are being considered in the sustainable battery technologies, okay, like some academic research sites, there are some industrial requirements, okay, like real energy density, they want mostly industry side, they will go for performance based, they will want to enhance, ramp up the effectiveness, whereas academic research, once they have already worked upon the performance, now they are going towards the sustainability side. So these things are there. Now coming to the last section towards the policy and regulation. So many countries, many continents, developed or developing nations are all coming together to work towards um, different battery policies, like European Union, they in 2023 they given a directive like requires minimum recycled content by 2030, so 16% of cobalt, 6% of lithium, 6% of nickel, okay, then extended producer responsibility, so the life expectancy of the battery should be also enhanced by the manufacturers. So mandates manufacturers to handle battery collection and recycling. Once the battery usage is over, we can sell it back or we can send it back for recycling to the same manufacturer. Similarly, US based energy department, they are also funding. Lot of research work is also going on in the sustainability battery R&D technology, like industry initiative Tesla and reused materials, closed loop recycling they are monitoring. In Sweden, a company called Northvolt, so world's greenest battery with 50% content can be recycled. So this is considered to be one of the biggest achievements, like 50% can be recycled means it's a big thing. Then Kettle, like Kettle, you can see leading sodium ion based commercialization batteries, and it is also not depending on the rare earth material. So definitely it is enhancing the availability, cost effectiveness and all. So life cycle assessment. So we should not consider the battery effectiveness or sustainability factors just by its operational use, right from the extraction to the end of the life disposal. So all factors need to be considered, like measuring cradle to grave. Cradle means that hole that we are digging because of the mining activities. So extraction from the ground to disposal into the ground, that impact need to be considered. Whole life cycle assessment. The key metrics should be carbon footprint, water use, recyclability, critical material dependence and all. So these are the things that we need to consider. So this diagram also depicts the similar things. Suppose in European Union this is shown, some ways to build better, more sustainable batteries, like use resource efficiently, supply chain should be ethical, no child labor, no involvement of mafia, no monopoly should be there, sourcing without geopolitical risk, use low toxic materials, okay, make them easy to recycle and reuse, then enable excellent round tripping efficiency. So efficiency of the battery should be enhanced, then second life use should be there, and the manufacturing should also be done using renewables. So make them energy density, ensure long lifespan. So all these factors are adding to gradually small contribution and making the battery moving towards the more sustainable usage. So in summary, we can say sustainability in battery technology spans right from the raw material sourcing to manufacturing and to the usage and recycling. So the complete cradle to grave, so whole cycle need to be considered. Then innovations in chemistry, like already mentioned some emerging trends, like so so solid state which does not involve any liquid electrolytes, then sodium based, abundantly available, low cost, then processes like green manufacturing, usage of renewable based electricity, then policies like circular economy mandate. Some government can impose compulsory rules and regulations on the manufacturers to work towards the circular economy, recyclability, think towards such things. Then future outlook that we can say, expect more localized supply chain to reduce geopolitical risk. So any country does not want to import the rare earth materials from other nations. So that should be done at a local level itself within the country. Growth of recyclable industry with economic incentives, movement towards net zero batteries. Okay, net zero batteries means emissions should be becoming zero right from the production, usage, and recycle sustainability. So in the final note that I will like to conclude that sustainable battery technologies are not just a technical challenges but an interdisciplinary one involving, so it involves multidisciplinary students and researchers like engineering, environmental science, economic perspective, and policy making. So as future engineers and researchers, we should focus on innovations and responsibility. Innovations in the sense performance can be upgraded. Responsibility means it should be sustainable. We should not harm the environment for our selfish requirements. So that we need to think of our upcoming generation also. So with this, we will I will conclude this session, and we will again meet in the next lecture. Thank you.